Hello, welcome to another edition of Bed Talks, TED Talks from my bedroom. I hope you're doing well. If you're wondering, it's a fun note today. On March 30th is actually Natural Virtual Vacation Day, and that's kind of what we had to do now. So I just wanted to kind of, make sure that we're all on the same page here. How about that? We can go to San Francisco, have a good time. That's pretty nice. I've never been to San Francisco. It's really nice. But I guess we can kind of go back to this now. Regardless of that, I hope your first day of class are going well. And today what we're going to tackle is section 14.3, just kind of review a little bit of what partial derivatives are and getting yourself ready for what's upcoming here. So kind of looking forward and what the idea of partial derivatives are. Let's think about what the idea, the concept of a derivative is at the most basic sense back in Calc 1, right? So we had you get something like this, right? If I have some function f of x and y, and I asked you what the derivative was of this function, you would tell me, well, it's actually the slope at every single line, right? I would make a point, I can make a tangent line to that curve at every single point, right? I can make these different tangent lines, and the slope of that tangent line specifically was the derivative at that point. And we can plot that, right? That would be f prime. Now, here's the thing, though. If I have a two-dimensional surface, it's not a really, or even a three-dimensional, if I have a three-dimensional object, slope is not really well defined. Take, for instance, a very, very handy antibacterial wipes from BJ's. So if you understand here, if I start at this point, I want to find the slope at this point, what is it really saying? Right? What is it really saying? So the slope is not really well defined, right? As we kind of talked about actually a little bit before, and the idea of lines, right? The idea of lines, there's not really the idea of slope. There's a direction. Right, so if I go in this direction, I'm actually going down. My function's height's going down. But if I go in this direction, my height's not really changing. If I go in this direction, my height's changing in different ways. So it really depends on which direction you go. We can think about a derivative, right? The idea of slope. How fast is my function changing? That's what the idea of a derivative is. How fast is the height of my function changing at every single point? And we can think about the same exact way here, like actually telling you which direction I'm going in. So let's say I'm going in the x direction. In this case, my function height is probably going to be around 0. Right? My derivative is going to be around 0 here because I'm not really changing that much. But if I go here, it's probably going to be negative, right? Because I'm going in maybe in this case the y direction. With this in mind, we can actually start to define what a partial derivative is. And as we've done in class and thought about, the idea of the partial derivative then comes from this concept, right? So we have something called fx, which we'll call the partial derivative with respect to x. Now, we have a couple different notations for this. We also have this funky notation. This is called a del operator. It's not a d, right? Usually we have like d dx. If I have the thing, here's the issue, because f here now could be a function of two variables. If I have a function of two variables, I can't really use this prime notation anymore, because that prime notation tells me, oh, I'm only having one variable. So I need to have two variables. I have two variables here, so I need to have better notation. This subscript notation is something we use. This notation also we use. This is called, difference between Leibniz and Newton's notation for calculus. So this is called the del operator. So we usually say df dx. It's okay to say that still. But we usually say f sub x or f sub y, as we'll call it. And what does this really mean? This means here, as a reminder, that I am finding out fx in the most basic sense means if I go in the x direction, the positive x direction, 1 unit, approximately how fast is my function height moving? Is it moving down? Is it moving up? Is it staying the same? Right? What's the tangent line to that point? So if I make the tangent line at these individual points here, maybe like here, right? If you'd probably notice, if I make the tangent line, it's going downwards. Right? It's going downwards. If I make the tangent line going this way, well, my function height's not really changing at all. So that's going to be the idea, going in the x direction or going in the y direction. And we can calculate these things in a pretty similar way as we want to, kind of exactly as you want to. And I'll tell you the reason why. So let's take our function, for instance. Let's take a function that I've already kind of have here. So let's take f of xy as an example. Is equal to x e to the xy. And let's say I wanted to find the derivative with respect to x first. What is f sub x? Now, thinking about this more succinctly, what I'm basically doing in my XY domain, if I take a look at my XY domain, I'm taking a point, say a point right here, and I'm just moving in the X direction, but I'm keeping Y a constant, right? What I'm doing here is I'm taking in the X direction and making Y a constant. So what we're going to do is if I'm taking the derivative with respect to X, I'm going to think about Y being a constant. Imagine Y is just a number, right? In this case, if Y is just a number, let's say something like 2, right? You can think about this maybe as e to the, to 2x. I know how to kind of do this. I would have to, if I'm going to take this derivative, I would probably use, product rule here, because I have a function times a function, right? So to take my derivative here, I multiply I have the derivative of x, which is just 1 e to the xy. Now plus, what is the derivative of e to the xy? Well, what's the derivative of e to the 2x? If you'd agree, I just take the derivative of the top with respect to x, and this would just be 2e to the 2x. I just bring that down. In a similar way, y is a constant here. It's a number. So what we do is we take the derivative of this with respect to x. And doing that, I get a y. So I bring down my y now, and this becomes xy e to the xy. And this is the derivative of this function with respect to x, the partial derivative of this function with respect to x. In a similar way, we can calculate the derivative with respect to y. Now, if I calculate the derivative with respect to y here, if I do this, x does not matter. So I really only have one function, right? Imagine this is now something like, 2e to the 2y. This is a constant, so it really doesn't matter when I take the derivative. But now I just take the derivative of this top. If I take the derivative of this top, I'm gonna bring down a 2, right? In the same way, if I take the derivative of this entire thing, I'm gonna bring down an x. So I get x squared e to the xy. And so therefore, these are my two derivatives with respect to x and with respect to y. Now, if I want to think about interpretation, which is actually a really important thing to think about going forward, right? What does this actually mean physically? Well, if I let's say I want to think about what's happening at the point 0, 1. Okay, actually, maybe a little bit better. No, I'll take a look at 0, 1. That's fine. Let me take a look at that. If I calculate fx at 0, 1, I just plug in zeros and ones here. If you notice, this then becomes e to the 0. This thing becomes 0 times e to the 0. So therefore, this is just 1, because e to the 0 is 1. And similarly, fy of 0, 1 is equal to, well, it's just a 0 here, so it just becomes just a 0. So what does this say? This function, if I'm at this point, well, I should tell you the exact point, right? At f at 0, 1, just this function at 0, 1, would you agree is probably just 0? So there's a point on this graph, 0, 1, 0. So imagine you were standing at this point. I'm standing at 0, 1, 0. And I want to go in the x direction. How fast will my function height be going? If I go in the x direction, I'm going to be increasing at a rate of 1. I just go right in the x direction. Okay. If I go right in the y direction, if I just go right down my y-axis, I don't change my x at all, that's going to be a 0. And that should make sense. Why does that make sense? Look at this function. It's x e to the xy. So whenever I have x being 0, this entire function value is 0. So whenever I'm just on the y-axis, I should just be 0, right? So I'm not changing anything. My function height's not changing if I just go right in the y direction. I'm at that point. So with this in mind, this gives us some idea of what's happening with this function. Okay, cool. That's kind of the idea. Now we can extend this to multiple derivatives and go forward from that. And what we can do instead, we get some actually really interesting notation here based off of this. I'm going to just keep these up because we're going to use these in a little bit. But we can also start to calculate second derivatives and third derivatives and so on. But the second derivatives we'll tackle at the moment. So you can take the second derivative. We have something called fxx. We have a couple different options here. The second derivative in Calc 1 usually references concavity, right? If the second derivative was positive, it was concave up. Second derivative is negative, it will be concave down. Kind of thinking about that calculus. But now I have a lot of different options, right? I could take fxx. Maybe I can then take the derivative with respect to x twice. I can take the derivative with respect to x and then with y, maybe. maybe I could do f of y with respect to x, or maybe the double derivative with respect to y. These are called second partial derivatives. We will discuss these actually going forward in terms of the ways to figure out if a function's a critical point's a maximum or minimum. It's actually at the end of our whole class here. So these partial derivatives, which also do have some interesting Leibniz notation, what we usually do is we denote. You have this second derivative notation here. We say, okay, this is the function with respect to x twice. I'm taking the derivative with respect to x twice. Maybe something like this, though, is a little bit more challenging, right? If I have the second derivative, I think about this going left to right. This is the derivative with respect to x and then with respect to y. So this corresponds to something like fxy. I read from left to right, as you would just a regular, English language, left to right. And so these notations, what we do, honestly, it just tells us exactly what we want to do. So if I want to take the derivative with respect to x twice, I start with fx, and just take that derivative again, and so on. So as an example, we can do all these here. If you want to do them all out, fxx here, I'm just going to take the derivative of this function again with respect to x, letting y be a constant. If I let y be a constant here, I'm going to again get e to the xy. I'm going to let y come down again, y e to the xy. This guy here is actually going to have to do product rule again. X times y, the derivative of that with respect to x is just y e to the xy, plus the derivative of this guy with respect to x is going to be, I bring down a y again. So it's going to be xy squared e to the xy. Something like this. You can combine these two and probably make this really nice, and to say this is just 2y e to the xy plus xy squared e to the xy. Something like that. You can do this for all of them if you wanted to. But one interesting thing that I want to talk about is to show you what happens when I calculate fxy or fyx. Doesn't matter which direction I go. Right? It doesn't matter if I take the derivative with respect to x and then with y. It doesn't matter whether I take the derivative of y with respect to x. What we can see here is, let me take the derivative of this guy with respect to y first. Okay, I'm going to take this guy with respect to y. I'm going to take fx and then y. This derivative here would just be x e to the xy, right? Because the derivative of the top. Then here, I'm going to have to use product rule again. And I would get the derivative of xy with respect to y is just x e to the xy, plus the derivative of this guy with respect to this with respect to y is just going to be the x. So this becomes x squared y e to the xy. I can clean this up maybe a little bit better, and this can be 2x e to the xy, plus x squared y e to the xy. There you go, something like that. Now, but let's do this guy. Let's take the derivative of this one now with respect to x. Let's do fyx. This is something called a mixed partial derivative. A mixed partial derivative gives me this, for instance, fxx is just a regular second partial derivative. This is a mixed. I have two different, derivatives I have to take. Mixed partial derivatives can be really interesting. So if I again take this here, I'm going to take the derivative of this guy with respect to x. I again have to use product rule. Derivative of x squared is just 2x e to the xy. And then the derivative of this guy with respect to x is again just y, x squared e to the xy. And if you notice, these guys are the exact same function. So this then begs the question, is this true? Can we always do this? And the answer is almost always yes. Now, the issue becomes when the function is discontinuous. If the function is discontinuous around a disk, around a point, then the Clairaut theorem does not hold. This is actually Clairaut's theorem here, more specifically. So let me just write this really quickly. The idea is, just more formally, is that Clairaut's theorem basically says fyx is equal to fxy if f is continuous. Yeah, more specifically, you can kind of say at a single point, if f is continuous, if s is continuous around AB. What do I mean by around? Around means I can just kind of put like a disk. Okay. Let's say this is my point AB. I could put a disk around, and everywhere in this disk around there, any size, if all those points inside of that disk are, you know, continuous and defined, then I'm all good. So almost always, if your function is continuous, you're good to go. You can just pick whichever direction you want to go. And this holds. You can, if I want to go x, y, maybe one of them's easier. Like, it actually doesn't matter. So for instance, I mean, you can show how important this would be because you can just flip orders whenever you want. So for instance, if I had something like this, you know, something terrible, maybe of a couple of different, you know, of a couple different variables. I got multiple variables here. X e to the y x, you know, plus z, or something like that. And I asked you to calculate, you know, fx z. Well, again, here, everything's continuous. If I asked you to calculate fxz, for instance, I could just say instead, this could be the same as fzx, which I think is a lot easier to calculate. Because if I did calculate the derivative with respect to z, this has no z, so this is just 1. Well, this is just, if I take this, I would then calculate fz. Fz is just 1. Right? This entire thing is just 1, because this has no function of z. And so therefore, fzx is just 0. It would have been a lot harder for me to go x and then z. If I want x then z, I'll have to do it, you know, product rule again, and then I'll get 0 because there's no z there, but it still is a little bit quicker. So it's a little bit better. You can flip around if everything's continuous, and it's a lot better that way. This also is going to be helpful going into integration too, that you're allowed to flip things only to a very specific amount of places. All right, and lastly, what I want to tackle here is the idea of implicit functions, and the idea going back to actually kind of harkening back to what we did back in Calc 1, kind of. So as a reminder, if I had something like, let's say something like, you know, y squared, you know, maybe something like y squared x is equal to, you know, y to the third plus x to the third, and maybe I know that y is a function of x, you know, and I wanted to solve for this. I want to solve for y prime. Let's say I want to solve for y prime. You know, I can't solve for y explicitly here. So what I could do is I could solve it for it implicitly. And what we did is we kind of realized if I want to take the derivative of both sides with respect to x, what I did is I took the derivative of both sides with respect to x. Maybe here I would then use the product rule. But I have to remember, product rule here, is that when I bring this down to xy, I get a y prime out of it, right, by using the chain rule. And you can do the same thing with this side, right? This becomes 3y squared, y prime, plus 3x squared. And then what we can do from here is I could just solve for y prime if I wanted to, and then, you know, get everything over to one side, you know, divide over it and solve out for y prime. It's going to be implicit, but it's okay if they don't know that. You can do the same exact thing in multiple dimensions. So in the same way, let's kind of say that I tell you that, you know, z is a function of both x and y. Okay, and I have something like xyz is equal to e to the z, something like that. And I want to find dz dx and dz dy. I want to find the derivative of z with respect to x and y. How is z changing with respect to x, and how is z changing with respect to y? As I move these things, as I move x and y, how is my height changing? And so if I want to do this, let's tackle this first one, and we can do the second one pretty quickly after that. What we can do here is I could take the derivative of this entire function, xyz, is equal to d dx, e to the z. Now, I want you to remember here, y is going to be a constant, z is a function of x. So what we have to do is, in this case, I have a function of x, we can call maybe yx, and I have a function of x again, which is a, you know, z. So I have to kind of use product rule again. The derivative of x, z, yx is going to just be y, z, plus, now I just get xy, but now the derivative of z with respect to x is dc dx. Here's that guy. Maybe I can think about this a little bit. Maybe I can write this a little bit more better with, using z sub x or something like that. That's okay for right now. Over here, the derivative of e to the z, again, z is a function of x. So if I think about e to the f of x, what I do is I bring down, f prime of x, e to the f of x usually. So I take the derivative of that z, which is just dz dx, e to the z. And now what I do is I simplify this by moving the zx over. Yz, I want to get zx by. If you see here, I can factor out a zx. I will just have an e to the z. Here, if I subtract this over, I would get x times y. And so therefore, dz dx would then be equal to y times z divided by e to the z minus xy. And this right here gives us at least an idea of how z changes when I change y. It's highly dependent on what z is, which makes sense because we don't have an explicit, but this is implicit. This is saying that if I know what z is, I know how z is changing with respect to x and all that. And you can do the same exact thing with y. It would look very, very similar to this. I think the only thing that would really change, if I'm thinking about this right, would be probably this y would change to x on the numerator. And that would be it. So that's the idea. So kind of going overarching here, 14.3. The idea is going to be that I have partial derivatives. The idea of partial derivatives, again, is that I'm going in different directions. We don't have the idea of slope anymore, at least formally defined. But we can think about go in a certain direction. If I walk in a certain direction, which is going to be, how is my height changing if I walk in a certain direction? How is my height changing if I do that? And that's the idea. So second derivatives can think about concavity. And we can, again, kind of go about and do multiple derivatives. And we can also find some implicit functions in the same exact way that we have in the past. Okay, so that's kind of it. Let me know if you have any questions about this. This is a good material and stuff that you're definitely going to need going forward. We're going to be taking partial derivatives basically from the end of the class. So it's important to kind of do this. And if you have any questions, let me know. As a nice aside, I have a joke for you. What did sushi A say to sushi B? Wasabi. All right, I like sushi. So hope you have a great day. Enjoy your virtual vacation day, and I'll see you soon.